Hello and welcome. So we are continuing with our second chapter which is on ammeter, voltmeters and ohm meters, and in this particular video we will talk about rectifier based voltmeters and ammeters, so that we can measure AC as well. Okay. So, okay, the reason we are considering this is, okay, let's recall what are the instruments that we have studied. We have studied PMMC instruments, we have studied electrodynamic and moving iron instruments, okay, and we know that PMMC can measure only DC, okay, and this can measure either DC or AC in principle. So, in principle this can measure both DC and AC. Also this can measure both DC and AC, but generally, as we have seen, generally this instrument is not used for measuring DC. Okay. So, this is used mainly for AC. In principle it can measure DC, but we do not use this for DC measurement because of the retentivity or residual magnetism problem which we have discussed before. Okay. So, this is mainly for used mainly for AC. And now if we compare PMMC and electrodynamic, recall that we have said that PMMC is more sensitive than electrodynamic, particularly for low values of current or maybe voltage. Okay. This is because PMMC has a permanent magnet, this does not have a permanent magnet, and the magnetic field in this instrument is again created by the unknown current. Therefore, if the current is low, in this instrument electrodynamic, both the magnetic field and current, both of them becomes low. So, the torque becomes lower. Here at least the magnetic field flux density B is not changing. So, B is always same, current is low for low currents. So, this is not the torque in this instrument is not as low as electrodynamic instruments. Okay. Therefore, PMMC instruments have some advantages, like this is more sensitive to low value of the current, but it cannot measure AC. Now, we can use PMMC, so which is a DC meter instruments in conjunction with or along with rectifier circuits, okay, so that it can measure both it can measure AC as well as is more sensitive, particularly when we are measuring low values of current. Okay. So, therefore, in this video we will talk about rectifier based meters. Now, rectifiers, you may already have studied rectifiers in your first year or maybe in your earlier courses, but let us recall it. Okay. So, generally we can have two types of rectifiers, which we call as full wave rectifier and half wave rectifier. Okay. So, we will come to the circuit in a while. Till then, let us see what they does. So, if I give an input which is sinusoidal, okay, so this is input, for full wave rectifier the output will be like this. But for half wave rectifier, for the same input, it will look like this. So, rectifier is a circuit which takes sinusoidal input and gives output which is like this for full wave rectifier, and for half wave rectifier it will be like this. Positive halves will remain unchanged, negative halves will become 0. So, positive half as it is, negative half is going to be 0 here as well, and in this case positive halves are unchanged, negative halves are reversed. Okay. So, this is what a full wave rectifier and a half wave rectifier does. Now, let us call this waveform as say this waveform is Vm sin omega t. Okay. So, Vm is what is the peak value of the voltage or current. Okay. So, let me call it Am, because it can be voltage, it can be current in general. So, let me call it Am. So, Am is this much, okay, and here again this will be Am. This output you can write it as possibly mod of Am sin omega t. In this circuit also this is Am, peak value. Okay, so this is the peak value, and let me just use A for simplicity. Okay, so here also it will be A. Okay, so the peak value is equal to A for both input and output. Okay. Now the RMS value, root mean square value, will be A by root 2. Once again, this is true for both input and output. Okay. So I guess you know how to find the RMS value of a sinusoidal wave. And the average value, okay, so for input is 0 because it's positive for half of the times, negative for half of the times. So for input, and for output this will be A by pi by 2, okay, for output. Okay. Once again, I am assuming that you know how to find the average value by integrating over a complete cycle or half cycle. You can do it. So in this case, peak is, once again, if peak is A, then RMS will be how much? It will not be equal to okay. So peak is A for both input and output. RMS is equal to A by root 2 for input, but will not be equal to A by root 2. Okay. So exercise, what will be the value? Okay. Homework, find out the value of the RMS for half wave rectified waveform. Okay. And then average, this will be A by pi by 2. Okay. It was for this full wave rectified waveform, and now in this case we see that half of the times the waveform is absent, like here it was present, here it is absent. So the average will definitely will be reduced by a factor of 2. So this will become half of this. So this will be A by pi. Okay. So this relationships you should be able to derive it on your own, and you should remember it always, okay, throughout this course. Okay. So particularly important relationships are this average value equal to this for full, that is, this is for full wave, this is for half wave. You must always know this. Now say I want to measure a AC voltage. Okay. So next the goal is to measure AC sinusoidal, purely sinusoidal, to measure a AC voltage with a DC meter, PMMC meter, with a PMMC meter. Okay. So this is the goal. How can we do that? We just need a diode. So now let's draw the circuit. Suppose I have a complicated network which I am drawing like a box, and it has two terminals between which I want to measure. So I want to measure the voltage between these two terminals. What do? I generally connect a voltmeter. Okay. So now we have to connect a DC voltmeter which can measure an AC voltage. So this voltage is AC. So this voltage is AC, purely sinusoidal. We have to measure it. Okay, so how we will do it? We will take a PMMC meter. Okay, now if we connect it like this, so the voltage is positive for half of the time, negative for other half. That means the current which will flow through this meter is positive in for half of the time, negative for other half of the time, and therefore the torque will be towards the maybe towards the right for one half of the time and towards the left for another half. And the average torque will be 0. If the frequency is high enough, then the pointer will not move at all, so this meter will not work. So that was a quick recapitulation why PMMC meter doesn't work with AC. But what we will do now, we will put a diode in this circuit like this. So now what happens? So if this is the input, this is the input voltage. Okay, this plus minus doesn't mean this is DC. This is only the reference direction for drawing the waveform. Okay. So I am measuring the potential of this point with respect to this point, and the waveform looks like this. And now the current which will flow through this meter, I. Okay, so this is the voltage, call it V. So this is VAC sinusoidal. The current which will flow through this meter will be positive here. In the positive cycle, current will flow as it is. So the current will be proportional to the voltage, assuming the meter is resistive. So the meter resistance is Rm. So meter is resistive. So the internal impedance of this meter is like a pure resistance with the value of Rm. So this current I will be, so if I call this as V peak, okay, then this value I peak will be equal to V peak divided by Rm. So this is sinusoidal, and the peak of this sinusoid is V peak by Rm, V by I. Here it will be 0, here it will be positive again, and again here it's 0, 0 like that. Okay. So if so, okay, now how should I calibrate or mark the scale of this meter? Okay. So say how should I calibrate this meter? Now okay, so if I assume this is the scale of the meter, and so this is a PMMC meter which I can mark for which I can mark the scale in terms of current. Say this current is 0, left side, right side is will be as per the notation IFSD, full scale deflection current, and let's assume that full scale deflection current is equal to 10 milliampere. Okay, and say Rm, so let's say FSD, full scale deflection current, is 10 milliampere for this meter, and Rm is equal to say 100 ohm. Okay, so that means this point corresponds to 10 milliampere, and this point corresponds to 0 milliampere. So this is a PMMC meter, that means the scale will be linear. So this point corresponds to half of FSD, that means 5 milliampere. this point is 2.5 milliampere, this point is 7.5 milliampere, and so on. But now I want to mark the scale in terms of the voltage, unknown voltage. Okay, so this is scale in terms of the current. Okay, so I want to mark the scale, the same scale I want to mark in terms of the voltage, so that by looking at the pointer position I can find the value of this voltage directly. Okay, so this point 0 current means definitely the voltage must also be 0. So this point I can write it as 0 volt. Okay, now what should be the value here in terms of voltage? So let's do the calculation. So here the current that is flowing is IFSD or 10 milliampere. Okay, so current is 10 milliampere, and this current is, so this is what? This is actually the average current. Okay, because this meter it is a PMMC meter, so this will indicate the average value of current. So here we can write, so this point, at this point average current is equal to 10 milliampere. Okay, so I average here is 10 milliampere. Now what is the value of the current, actual current? This is a time varying current IT, and this IT looks like this. Okay, and therefore if the peak of this current is IP, then I average, we can write, how much will it be? This will be I peak divided by pi. Just recall from the previous slide. This is half wave rectified. Okay, so this is I average. Now here I average is 10 milliampere, which implies I peak by pi is equal to 10 milliampere here. Now what is I peak? I peak is equal to V peak by Rm. This is equal to 10 milliampere. Okay, so we can write V peak is equal to 10 milliampere multiplied by Rm. Rm is here 100 ohm. So 100 times 10,000, so this will be 1 volt. Okay, this is V peak. Okay, so V peak is 1 volt. If V peak is 1 volt, now that means this is 1 volt. So this will be 1 volt. Okay, so let's not write it here. So then the RMS value of that voltage will be by root 2. So therefore this position I should mark it as root 2, whatever the value is, it's like 0.707 or so. This will be V volt. Okay, so this is the value or scale in terms of voltage. What kind of voltage? RMS voltage. Very important. This is not in terms of peak voltage. This is in terms of RMS voltage. Okay, and you probably know that when talking about AC, particularly sinusoidal AC, RMS quantity is generally what we use to mention it. So this scale is in terms of RMS voltage. This scale was in terms of current. Okay, to be more accurate, this was in terms of the average current. Okay, so this is in terms of average current, this is in terms of RMS voltage. and if so, the half of it. So, the center point I can definitely mark it as 2√2 volt and so on. So, this is how the scale should be marked, and this is how the circuit should look like. Okay. So, this is a half wave rectifier based voltmeter. Okay. So, we will call this thing together as my voltmeter, because I will have the terminals here where I will connect the unknown voltage. So, this is a AC voltmeter which is made up of a diode and a PMMC meter. Okay. Now, suppose let us take a next new problem, new question, where the goal of our goal is now to measure say an AC voltage and an AC current with a PMMC meter. Okay. So, I have a network in short NW in which I have a particular branch and some current is flowing through it. Call this current as I, and I want to find out the value of I. This is AC and purely sinusoidal. Okay. Now, so to measure this current, I have to insert a PMMC meter. Why PMMC? Because PMMC we know is more sensitive than other types of meters. So, we connect a PMMC meter just one small note is that this symbol where we have an arrow inside a circle, please do not think that this is a current source. Okay, this is also, we use the same symbol for meters often, but the only difference, okay, it's generally when talking about meters we indicate the pointer at an angle generally, but for current source we generally write it, we draw it like this. So, this is current source. So, please do not get confused, this is generally a meter. So, this is I mean this is bit confusing, we use the same symbol for both of the elements. I guess the meaning of the symbol will be clear, evident from the context, or it is always better if we write what it is beside it. So, this is a PMMC meter, that means this is a DC meter, of course this is a DC meter, and we are measuring a AC current. This current is AC. So, the deflection will be 0 if I connect it like this, because half of the times current is positive, half of the times it is negative. So, half of the times torque is positive, half of the time it is negative, average torque will be 0, pointer will not move at all if the frequency is high enough. So, the solution is put a diode in this circuit just like the voltmeter circuit we used previously, and then the current will flow for half of the time and the meter can indicate some non-zero value. Now, this circuit is wrong. This circuit, if I call this circuit an ammeter, okay, this as an ammeter is absolutely wrong. Okay, never make an ammeter like this. Why? Because this was the original circuit, and here the current was flowing like this. It was flowing for both positive and negative halves. This is the circuit where we have cut open this branch and inserted an ammeter, and this ammeter is allowing the current to flow only for 1/2 of the time. It is not allowing the current to flow for the remaining time. So the original network is changed, is disturbed, okay, because in the original network the current was flowing always, but now in this circuit when we are trying to measure something, we have changed this circuit completely. So we have mistakenly changed the original circuit. Okay, so whenever we measure, whenever we insert any instrument in any measuring instrument in any circuit, the original circuit should not change. Okay, so if we want to measure something, we should not change that itself. Okay, so this is true for any measuring instrument, electrical engineering, in any other discipline, everywhere. If we are trying to measure something, we should not change that while measuring it, but in this circuit we are doing that. Okay, so therefore this is a wrong circuit. The correct circuit should look like this. So if this is the network, this is my meter. Okay, I will put a diode in the opposite direction like this, and this will be my AC ammeter. This is my AC ammeter. So now what happens? This current I can flow always. Half of the time it flows through the meter, half of the time it flows through this diode, but it can flow always. So here this I will flow always. So therefore the original circuit is not changed, but the meter gets current only for half of the time. So I is continuous. This is I, but if I call this current as IM flows only here. This is IM. So therefore the average value of the meter current is non-zero, because negative current doesn't flow through the meter. So meter will indicate some value, but the circuit is not disturbed. So this is the correct circuit, correct ammeter. This is a wrong ammeter. Never make an ammeter like this. For voltmeter, okay, so previously for the voltmeter circuit, we didn't put a diode in the opposite direction. That's not so necessary, because voltmeters are ideally not supposed to draw any current. So ideally very little amount of current flows through this in the positive cycle, and the lower the amount, it's better. We know the voltmeter should have very high resistance, very high impedance, and in the negative cycle no current flows, no problem, because in the original circuit as well no current was flowing between this. So for voltmeters the diode in the opposite direction is not that important, but for ammeters definitely we need it. Okay. So now We will take a break in this video. We will continue with this topic, and we will discuss more about say full wave rectifiers, full wave rectifier based circuits. Will deal with more problems examples in coming videos. Thank you.